Hello, everyone. My name is Marcia, and I'm excited to share my final project with you. This presentation explores how physical activity and age influence body mass index, BMI, and obesity status among US adults by using NAME's data set from 1999 to 2010. The goal is to apply multilinear and logistic regression methods to identify key pre- predictors of obesity and contribute data-driven insight to the field of public health prevention. These findings will be interpreted through the lens of applied biostatistics and informed by real-world relevance for community health initiatives. The objectives of this presentations are and analyze how physical activity and age predict BMI using multilinear regression, determine whether demographic and lifestyle factors predict obesity status using logistic regression, using NAIN's 1999 through 2010 data to identify significant predictors of weight-related health outcomes in US adults, interpret SPSS regression outputs including coefficient, p-values, odd ratios, and model diagnostics. Finally, I'll apply these findings to support public health strategies and aim at promoting physical activity and preventing age-related obesity. Understanding obesity is an epidemic. Obesity remains a significant public health crisis in the United States. The rates of obesity have steadily increased over the last several decades. Obesity contributes to high risk for heart disease, diabetes, and certain cancers. Understanding behavioral and demographic predictors of obesity is essential for effective intervention. Obesity continues to affect over 42% of adults in the United States, contributing to increased risk of type 2 cardiovascular disease, type 2 diabetes, cardiovascular disease, and premature mortality. Tackling this health issue requires a clear understanding of both modifiable and non-modifiable risk factors. This slide this slide introduces two key modifiable behaviors. Physical activity and diet, with a particular focus on how physical activity interacts with age, a non-modifiable factor. Physical activity is well documented in the literature as a protective behavior that helps regulate weight and reduce the risk of obesity-related conditions. However, the benefits of physical activity can be limited by age-related challenges, particularly among older adults who face mobility constraints or chronic illness. To examine these relationships, this project used um, NAIN's National Health and Nutrition Examination Survey. It is a nationally representative data set that combines physical examination with interview-based health data, making it ideal for analyzing health trends across diverse U.S. populations. It allows for robust comparison across age groups, racial, ethnic backgrounds, and socioeconomic levels. The purpose of this review is to show how prior studies support the importance of analyzing physical activity and age as predictors of obesity. These findings may help lay these foundations for the regression models used later in the project and demonstrate the value of evidence-based interventions that target modifiable behaviors within specific population subgroup. Physical activity plays a critical role in regulating weight and reducing the risk of chronic disease associated with obesity. Research consistently shows that lower levels of physical activity are linked to higher BMI and an increased risk of conditions such as type 2 diabetes and cardiovascular disease. With aging, individuals experience natural decline in metabolic rates, muscle mass, and mobility. These age-related changes can lead to gradual weight gain, especially when physical activity is limited. At the same time, engaging in regular physical activity helps maintain energy balance, improve insulin sensitivity, and support cardiometabolic health. However, not all adults have equal access or ability to remain active. Older adults and underserved population often face greater barriers to physical activity, including environmental, financial, and physical limitations. As a result, they may be at a greater risk for obesity related complications. Public health efforts must take these disparities into account when designing intervention. Supporting physical activity across the lifespan and especially among vulnerable population is essential to reducing obesity and improving health outcomes. This evidence supports the use of age and physical activity as independent predictors in this project's regression analysis and aligns with public health goals aimed at promoting equitable, evidence-based strategies for obesity prevention. Physical activity is a well-established modifiable factor linked to both body mass index and obesity-related health risks. Individuals who engage in lower levels of physical activity are more likely to have higher BMI and a greater likelihood of developing chronic diseases. Age also plays a significant role. As a person gets older, they experience physiological changes such as decline in metabolic rate and muscle mass that contribute to gradual weight gain over time. These biological factors are often worsened by mobility limitations or chronic illnesses, which reduce the ability to stay physically active. Names-based studies show that physical activity level tends to decline with age and that BMI often increases as activity levels drop, particularly among sedentary groups. Importantly, even moderate intensity exercise such as walking has been shown to improve BMI and overall cardiometabolic health. These findings underscore the importance of promoting and maintaining a physical activity through the lifespan. Supporting individuals, especially older adults, in staying active can serve as an essential strategy for both obesity prevention and chronic disease management. My first research question explores whether physical activity level and age are significant predictors of BMI among US adults. The question rooted in public health evidence that shows both lifestyle, behavior, and demographic characteristic contribute to weight status. The null hypothesis states there is no statistically significant relationship between physical activity, age, and BMI. In contrast, the alternate hypothesis posits that both physical activity level and age are statistically significant predictors of BMI. To analyze this question, multilinear regression was used. This method allows for the examination of how each independent variable, physical activity, and age relates to BMI while holding the other variable constant. This also helps determine the strength, direction, and statistical significance of each relationship within the predictive model. Understanding how these factors interact provides valuable insights into obesity prevention strategies, especially for adults at risk for weight related health complications. These findings from this analysis can inform interventions that target modifiable behavior like physical activity while recognizing the non modifiable influence of age. Analyze my research question one. A multiple linear regression was conducted to examine how age and physical activity level predicts BMI among US adults. The dependent variable in this model is BMI, measured as a continuous variable. The independent variable includes age, also continuous, and physical activity, which was dichotomized into variable into the variable activity. I labeled activity bin 18 to reflect whether participant engage in moderate to vigorous activity. This model allows us to explore whether these predictors have a statistically significant and independent association with BMI after controlling each group. The analysis was conducted using a sample of 613 participants drawn from names data set. Using this regression framework, we can estimate how much of the variation in BMI is explained by physical activity and age, and whether these relationships are strong enough to inform public health strategies aimed at obesity prevention. The scatter plot illustrates the bivariate relationship between age and body mass, age and BMI. A moderate upward trend is visible, suggesting a positive linear association. As age increases, BMI tends to rise as well. This pattern is consistent with the findings in public health literature, which attribute weight gain in adulthood to both physiological changes, such as declining metabolism, and muscle mass, and lifestyle factors. While scatter plots alone do not establish causality or statistical significance, they're essential for checking whether the relationship between predictors and outcomes follow a linear pattern, which is a key assumption for multilinear regression. In this case, age is treated as a continuous variable, which supports its inclusion in the regression model without the need for dummy coding. Scatterplots should only be used when age is analyzed in this form to avoid misleading visual patterns due to artificial grouping. This visualization provides preliminary support for model assumptions and helps justify the use of age as a continuous independent variable in the analysis of BMI outcome. Descriptive statistics help summarize the characteristics of the analytic sample used to evaluate the first research questions. Out of the NAINS dataset, 613 participants have completed data for both age and physical activity. Among them, 39.1% were classified as physically active, while 60.9% were not. A substantial number of cases, over 61,000 participants, were excluded from the summary due to missing responses for the physical activity variable. For the continuous variable, the mean age of the sample was 51.6 years, with a standard deviation of 19.4, indicating a wide age distribution. The mean BMI was 27.3, placing average participant in the overweight range and based on CDC classification. A Pearson correlation coefficient was calculated to assess the linear relationship between age and BMI. The result was R equals 4.75, P, which is P is less than 0.001, indicates a moderate positive correlation, suggesting that as age increases, BMI also tends to increase. This statistically significant association supports previous research, shows that weight gain is more common with advancing age, often due to changes in metabolic rate, physical activity, and functional capacity. These descriptive findings provide initial evidence that both age and physical activity may play a meaningful role in predicting BMI, supporting their inclusion in the multilinear regression model presented next. A Pearson correlation analysis was used to examine the linear association between age and body mass index. The results R equal 0.475, P less than 0.001 indicates a moderate positive correlation, suggesting that age increases, BMI tends to increase as well. This relationship is statistically significant and unlikely to have occurred by chance. It supports findings from previous research showing that age is a key predictor of increased adiposity, adap, adap, adiposity in adults, likely due to metabolic changes, reductions in physical activity, and shifts in body composition that occur over time. This result strengthens the rationale for including age as a continuous independent variable in the multilinear regression model. By identifying the strength and direction of this relationship in advance, the correlation analysis helps ensure the model assumptions are met and that age is appropriately interpreted within the context of BMI prediction. The multilinear regression model examined how well age and physical activity together predict BMI. The model yielded an R2 value of 0.222, which means that approximately 22% of the variance in BMI is explained by the combination of these two predictors. This level of explained variance suggests that age and physical activity have a meaningful but partial influence on BMI, indicating that other factors not included in the model may also contribute to BMI outcomes. The model was statistically significant overall with an F-test result of F 2, 6.10 equals 87.240, P less than 0.001. This means that the likelihood of obtaining these results by chance is extremely low, confirming that relationship between the predictors and the BMI is not random. These findings support the interpretation of both age and physical activity play a statistically significant role in explaining BMI differences among U.S. adults. This justifies further analysis of each predictor's individual contribution in the next step. The regression analysis provides the final equation used to predict BMI. Based on age and physical activity level, the model expressed as BMI equals 14.197 plus 0.673 age minus 0.485 physical activity. Each coefficient represents the average change in BMI associated with a 1-unit change in the predictor variable holding other variable constant. Age was statistically significant predictor of BMI. For each additional year of age, BMI increased by approximately 0.673 units after adjusting for physical activity. This finding reflects the well-documented trend of weight gain with age, likely due to metabolic and behavioral changes. Physical activity, on the other hand, was not statistically significant in this model. P equals 0.146. While the direction of the coefficient was negative, suggesting that active individuals may have lower BMI, this effect did not reach the threshold for statistical significance in this analysis. These findings emphasize that age plays a stronger role than physical activity in predicting BMI within this sample. This does not mean physical activity lacks importance. Rather, it may suggest that its relationship with BMI is more complex or influenced by other measurable factors. The results may help inform public health messaging by reinforcing the importance of early intervention that address age-related obesity risk. Outliers diagnostic was conducted using standardized residual to evaluate whether an extreme value unduly influenced the regression model. The standardized residual ranged from approximately negative 1.88 to positive 5.87. While the upper limit is relatively high, no residual exceeded the commonly accepted outlier threshold of plus or negative 3.0 for leverage or influence, suggesting that the model was not significantly skewed by extreme data points. This check supports the assumption of normal distribution of residuals and helps confirm the internal validity of the model. Additionally, a confounding check was performed by including gender as a third variable in the model. The regression coefficient for age and physical activity changed only minimally after adding gender, indicating that it is not an act as a co-founder. It did not act as a co-founder in the relationship between these predictors and BMI. Together, these results enhance confidence in the stability and reliability of the regression findings and support the integrity of the final model used to answer research question 1. Evaluated whether gender acted as a co-founding variable in the relationship between age and physical activity and BMI. Two regression models were compared. Model 1 included only age and physical activity as a predictor, while Model 2 added gender to the model. In Model 1, the coefficient for age was 0.673. After adding gender, it changed slightly to 0.676, which represents a 0.45% change. Similarly, the coefficient for physical activity changed from negative 0.485 to negative 0.484, reflecting a 0.21% change. Since both changes were well below the 10% threshold typically used to identify co-founding, gender did not meet the criteria to be considered a confounding variable. This means that the association between BMI and the two primary predictors, age and physical activity, remains stable and interpretable, regardless of gender. As a result, gender was excluded from the final model to preserve parsimony and maintain a focus on the variables most relevant to the research question. In conclusion, this analysis examined whether age and physical activity level significantly predict BMI in US adults using a multilinear regression. The findings provided partial support for the alternative hypothesis. Age emerged as a statistically significant predictor of BMI. The regression coefficient for age was B equals 0.673, P less than 0.001, indicating that BMI tends to increase as individuals get older. This is consistent with prior research on age-related metabolic changes and decreases physical activity in older adults. Physical activity, while negatively associated with BMI, was not statistically significant in this model. B equals negative 0.85, P equals 0.146. Although the direction of the relationships aligns with expectations, suggesting that more active individuals may have lower BMI, the result was not strong enough to confirm a meaningful independent effect. The model explained 22.2% of the variance in BMI, R squared equals 0.222, reflecting a modest but meaningful amount of explanatory power. A confounding check showed that gender was not a confounder, as the inclusion of gender in the model changed both coefficiently by less than 1%. One outlier was identified but retained, as it does not meaningfully distort the model or violate the regression assumption. In summary, age was more consistent and statistically reliable predictor of BMI in this data set than self-reported physical activity. These findings reinforce the importance of integrating age-related risk factors into obesity surveillance and intervention strategies, especially as the population ages. My next question um, was used with linear logistic regression model, focused on the association between age, race, ethnicity, and the odds of being classified as obesity. And remember, to be classified as obese, you have to be greater than 30. After removing non-significant predictors, the model retained only the variables that showed statistically significant association, age, and identifying as other Hispanic. The analysis showed that as age increased, the odds of obesity also increased. This trend was especially apparent among adults aged 40 and older, reflecting physiological shifts as slow metabolism, muscle loss, and reduced physical activity, which contribute to weight gain with age. In addition, individuals identifying as other Hispanic had significantly higher odds of obesity compared to non-Hispanic white adults who served as a reference group. This finding supports decades of research showing that racial and ethnic disparities in obesities are driven in part by inequities in access to nutritious food, preventative health care, and neighborhood level resources. While physical activity and gender were initially included in the model, they were excluded during stepwise refinement due to non significance. Their removal helped strengthen the focus on the most meaningful predictor without overfitting the model. In summary, this analysis found that older, age, and other Hispanic ethnicity were both significantly associated with increased odds of obesity. These findings underscore the need of culturally and age-appropriate culture appropriate public health strategies that address the unique barriers faced by diverse population through the adult lifespan. To analyze the second research question, I used the same data set names and conducted a binary logistic regression in SPSS. The goal was to identify whether age and race ethnicity was significantly associated with likelihood of being classified as obese. The dependent variable in this analysis was binary obesity status variable. Variable obesity bin 18 is how I classified it in my set, where a BMI of 30 or greater was coded 1, obese, and a BMI below 30 was as 0, not obese. The model initially included age, race, ethnicity, gender, and physical activity level. However, after running the regression, only age and race ethnicity remained significant. As a result, gender and physical activity were removed to reduce the overfitting and allow for a clear interpretation of the statistically meaningful predictors. Age was included as a continuous variable, while race was dummy coded into multiple groups. The reference category was non-Hispanic white, allowing for meaningful comparisons with other racial and ethnic identities. The model structure enabled a focused evaluation of the association between age, race, ethnicity, and obesity status. These methods helped isolate the most impactful predictors and provide a clear framework for understanding disparities in obesity outcomes. The final logistic regression model used to examine the association between obesity status and key demographic variables among US adults. This model was statistically significant overall, as indicated by omnibus test of model coefficient x squared equals 201.042, while p is less than 0.001, meaning the predictors included provided a better fit than a model with no predictors. A model performance was evaluated using several fit statistic. The Nagelkirk R2 value was 0.190, suggesting that the model explained approximately 19% of the variability in obese status. While this value is not high, it is consistent with what is commonly observed in public health and behavioral science research, where multiple environmental and structural factors contribute to complex health outcomes like obesity. Classification accuracy was 98.6%, which may initially appear strong. However, this is likely influenced by class imbalance in the outcome variable. Most respondents were classified as not obese. This type of imbalance is common challenge in epidemiologic studies and can lead to misleading accuracy rates. Despite this, the model successfully identified age and other Hispanic ethnicity as significant predictors of obesity and can still provide a valuable insight for targeting intervention. The Hosmer-Lemichaud test produced a p-value of 0.321, indicating that the model's predicted probabilities fitted the observed data well. This test is often used in a logistic regression to assess goodness of fit, and a non-significant result of p is greater than 0.05 means the model does not significantly deviate from the observed data. Taken it together, these results suggest the final model was statistically valid and had acceptable explanatory power and met logistic regression assumptions. This model can inform public health planning, and particularly for age-related and ethnicity-based disparities in adult obesity. This slide presents the adjusted odds ratio, X parentheses X parentheses B double parentheses, from the final logistic regression model for predicting adult obesity. Odds ratio allow us to understand how the likelihood of being obese changes with each predictor while holding all other variable constant. The results show that age was a statistically significant predictor of obesity, p less than 0.00101. The odds ratio for age was 1.817, which means that for every 1 year increased in age, the odds of being obese increased to approximately 82%. This finding is consistent with previous research showing that metabolic and behavioral changes with age, as reduced physical activity, slower metabolism, and increased fat mass, contribute to a higher risk of obesity in older adults. The model also identified other Hispanic ethnicity as statistically significant predictor, p equals 0.045, with an odds ratio of 2.414. This means that individuals in this group had more than twice the odds of being obese compared to the reference group, non-Hispanic white adults. These findings support well-documented disparities in obesity prevalence among racial and ethnic groups influenced by structural inequities in access to healthy food, physical activities, opportunities, and healthcare services. Other predictors that were initially included, such as gender, physical activity, and other race categories, were not statistically significant and were removed during the model refinement process. This helped avoid overfitting and ensure that only predictors with meaningful contributions to the outcome remain in the final model. Together, these adjusted odds ratios demonstrate how age and ethnicity interact with a multivariable framework to influence obesity risk. From a public health perspective, from a public health perspective, the results emphasize the need for targeted, culturally sensitive interventions, especially for older adults and Hispanic population, to reduce disparities in obesity-related health outcomes. Final logistic regression model identified two statistically significant predictors of obesity among US adults age and identifying as other Hispanic. First, age was significantly associated with obesity status. The odds ratio was 1.82, indicating that with each additional year of age, the odds of being obese increased by approximately 82%. This result aligns with prior research showing that age is linked to metabolic slowdown, reduced physical activity, and change in body composition, all of which contribute to weight gain over time. Second, individuals identifying as other Hispanic had significantly higher odds of being obese compared to the non Hispanic white reference group. The odds ratio was 2.41 with a p value of 0.045, more than twice as likely to be classified as obese. This findings reflects well-documented racial and ethnic disparities in obesity risk, which often shaped by social determinants of health, such as access to nutritious food, safe environment, economic stability, and healthcare services. The model overall performance measured by Nagelkirk R squared was 0.190. This means that the model explained about 19% of the variance in obesity status. While this level of explanation variance is modest, it is typical for behavioral and population level public health studies. It reinforces the idea that obesity is influenced by multiple factors, many of which extend beyond individual level characteristics. These results emphasize the importance of incorporating both age-related and culturally relevant considerations into public health strategies aimed at preventing obesity across diverse communities. Logistic regression model accurately identify predictors of obesity status. We evaluated whether gender and physical activities influence the association between age, race, ethnicity, and obesity. Both variables were initially included in the full model and then removed one at a time to assess changes in the odds ratio for age. When gender was excluded, the odds ratio for age shifted from 1.065 to 1.063, a minimal change of just 0.19%. Removing physical activity resulted in a similarly small change, reducing the odds ratio to 1.061. Since both adjustments were well under the commonly accepted 10% threshold for identified co-founders, we determined that neither variable had a co-founding effect. By removing these non-significant predictors, we simplified the model while maintaining the strength of our key findings. These refinements support a more interpretable and efficient analysis, allowing greater focus on the significant effects of age and race and ethnicity on obesity status. The final logistic regression model is identified. two statistically significantly predictors of adult obesity: older age and identifying as other Hispanic. Age was associated with substantial increase in obesity risk. With each additional year, the odds of being obese has increased approximately 82%, or 82%, which is odds ratio equals 1.82. P is less than 0.001. This aligns with research showing that metabolic rates slows, muscle mass decreases, physical activity level often decline as individuals age, all of which can contribute to increased adiposity. Participants in identifying as other Hispanic had significantly higher odds of obesity compared to non-Hispanic white adults. Odds ratio equals 2.41, P equals 0.045. This may reflect disparities in access to healthy food, culturally appropriate healthcare, safe physical activity environments, and economic opportunity, all of which are key social determinants of health. The model's Nagelkirk R square was 0.190, indicating that it explained about 19% of the variability in obesity status. While modest, this is typical of a logistic regression model explaining behavioral and environmental predictors in public health. An important limitation was class imbalance. Very few participants in the dataset were classified as obese, which may have reduced the model's ability to correctly predict positive obesity cases. Addressing this issue in future research may require weighted models and penalize logistic regression or stratify sample to improve prediction accuracy for underrepresented subgroups. Overall, these findings emphasize the need for age-sensitive and culturally responsive obesity prevention strategies, particularly those that address inequities affecting Hispanic communities and older adults. The first research question used multilinear regression. Oh, just to review, the first research question used multilinear regression to examine predictors of BMI as a continuous outcome. Age was the only statistical significant predictor, with BMI increasing slightly as age increased. Physical activity did not reach statistical significance and was not retained in the final model. My second research question used binary logistic regression to explore factors associated with BMI. After simplifying the model to include only significant predictors, age and other Hispanic ethnicity remained. Older adults were significantly more likely to be obese. Individuals identifying as other Hispanic had more than twice the odds of obesity compared to non-Hispanic white adults. The model explained 19% of variability in obesity status. Nagelkirk R squared equals 0.190, which is consistent with other health behavioral models. Physical activity and gender were both non-significant in the logistic model and were removed to avoid overfitting. These findings emphasize the importance of age and ethnicity-specific approaches to obesity prevention. Finally, this project used two regression models to explain predictors of adult obesity using NAN's dataset. The multilinear regression model for research question 1 shows that age was a significant predictor of BMI. Each additional year of age was associated with a 0.63 unit increase in BMI after adjusting for physical activity. Physical activity, while negatively related to BMI, was not statistically significant, which may reflect limitations in how activities were measured specifically through self-reported frequencies. For research question 2, the logistic regression model revealed that both older age and identifying as other Hispanic were significantly associated with higher odds of obesity. Participants classified as other Hispanic are more than twice the odds of being had more than twice the odds of being obese compared to non-Hispanic white adults. This finding is consistent with the research documenting structural inequities in access to nutritional foods, healthcare, and culturally relevant resources. The final model explained 19% of the variance in obesity, which is considered modest but acceptable in public health research due to the complexity of obesity related factors. A key limitation was class imbalance, which likely reduced the model's sensitivity to detect obesity cases. Future studies should consider applying weighted and penalized regression techniques to address this issue and improve model accuracy. From a public health perspective, the results emphasize the need for age-sensitive obesity prevention programs and culturally tailored intervention targeting Hispanic population, especially as the U.S. adult population continues to age and diversify. Thank you for attending my presentation, and here are my references. If you have any questions or concerns,